All right. Good afternoon. Thank you. Good afternoon. It sounds like the sound is working. We have a new microphone. That is wonderful. And just to start where we should start, my name is Dr. Mullner, and here's also Dr. Crowley in the room. And together we are moderating the MyResonex seminar, which is part of the Materials Resource Sustainability class, and our students are here in the classroom. We also have some guests in the classroom today, and we also welcome all of those who join us from remotely to the MyResonex seminar. And as always, I give a quick rundown how we do this after the introduction, or also the introduction of our speaker. Our speaker will give a 40-minute seminar. And at the end of that seminar, we will have a little bit of a breakout session. We're around tables here in the classroom. We discuss the discussion prompts that our speaker is giving us. And those zooming in will have the opportunity to join a breakout room to talk about those discussion prompts for 5 minutes. If you prefer to just be there in the main room, that's fine. After 5 minutes, we call you all back and we'll have a Q&A. And with that, it's now my pleasure to introduce our speaker, Greg Nelson. Mr. Nelson earned a Bachelor's of Science in Geophysical Engineering from the Colorado School of Mines, and then a Master's of Science in Geophysics from Boise State University. Go Broncos! While finalizing his graduate work at Boise State, Mr. Nelson began his consulting career in 2007. After several tedious years in environmental and litigation support on the East Coast, Mr. Nelson returned to Colorado, where he began supporting the mining industry and developed a passion for it. Over the past decade, he has spent the majority of his time either preparing NEPA baseline documents or preparing NEPA documents. He spent the past 5 years with Montgomery Associates working in their Intermountain division supporting mining-related projects. And today he will talk to us about hydrology in mining. Please help me welcome Greg Nelson.
How's that? Can you hear me? Good. Okay. I am a consulting hydrogeologist, and I'm in consulting probably because of my ADHD, meaning I can't work on a project longer than about 18 months. I have to keep switching up. And so there's a lot of work that I've done over the last 20 years, just jumping from project to project. I could not work for a single entity in that time or a single project. There are some people, perhaps some of you are that way, but that is not me. So a little bit of discussion about what I'm going to talk about today. I'll talk a little bit about who I am, where I came from, and why I do what I do. And I'll talk about several projects that I've been involved in. A couple of them are important to this class and to the kind of the textbook that you guys are reading in. I've had probably a third of the projects that are discussed in that book I've been involved in. I've worked in, or I know someone pretty well who's working in that field. I feel like I'm getting a little bit of feedback. Let me know if it's not loud enough. Okay, so from there, so my background. This is the Boise Hydrogeophysical Research Site, BHRS. It happens to be several miles up the Boise River towards the reservoir, just off of the green belt there. There is a well field that Boise State has installed there for research. My master's thesis was a numerical model of a tracer transport. So in one of these wells, they dumped in a bunch of brine water and they pumped it out of another well. And so my thesis was a groundwater, a computer model of how that brine flowed through the subsurface. I am a hydrogeologist. When you think of hydrogeologist, what do you think of? I study hydro, water, geo, groundwater. And when you think of groundwater, who here thinks of big caverns in the ground filled with water, kind of like this picture. Don't be ashamed. It's okay. I thought that too until I became a hydrogeologist. This does happen, but it's pretty rare. More than anything, it's in this instance. You've got a whole bunch of pores or little things, and they're filled with water, and the water flows through those pores. And so that's what groundwater is generally referred to. And beyond these little pores or these sand grains, you can think of it also as fractures. Solid rock that breaks, there's a little space in between in that fracture or fault, and it fills with water, and that's where groundwater is. So most of the mass in the ground is simply just mass, rock, detritus, whatever it is. The rest is fluids. And I had a wise professor once tell me, nobody cares about the rocks. And that hurt my feelings as a geologist, because I like the rocks. But he was right. Nobody really cares about the rocks. They care about what's in the rocks, and they want to get it out, whether it's water, whether it's whatever they're mining, or if it's the contaminant. They want to get it out of the rocks. So they just care about what's in it. So as a hydrogeologist, those tedious years at the beginning of my career were involved in environmental work. So where is this contaminant plume originating? Why is it underneath my site? Is it caused by me or the entity that has employed me? And where is it going? Now, I am a consultant in the mining industry, and I primarily focus on the ore body that they want to get out of the ground. It's beneath the water table. It's below the groundwater. They want to get at it. But mining in scuba gear is a little difficult. And so my job is to help them get the water out of the ground before they mine into it. So how much water needs to come out, and how to manage that water. Whether it's discharging the water or using the water. So water in mining. There's always a balance of these three issues. There's either too much water, too little water, or there's water quality problems with that. And oftentimes I find that all three of these problems are happening on the project at the same time. Some areas have too much water, others have too little, and there's always water problems. And so this is just kind of a conceptualization of water that's within the mine. So as a hydrogeologist, what tools do I have to answer the questions that are coming my way? There's geologic information. There's a lot of geologic maps. There's wells, drilling that happens. You can get a lot of information out of well logs, the drilling, the geologic information from that. You can instrument a well. You can measure how much water fills up that well, at what level. And that level will change depending upon what happens within the groundwater system. We can stress the system. That's what aquifer testing is. An aquifer is the underground strata or underground material through which water moves appreciably. And so we want to test those aquifers and quantify how well they allow water to flow through them. And so that's what aquifer testing is. Generally, it involves you drill a big well and you drill monitoring wells that measure water levels around that pumping well. That pumping well, that first well that you drill, you pump a lot of water out of that, and water levels change throughout the system. And then the last thing, and this is what I am primarily focused on in my career, is modeling. I develop and work on a lot of models of the groundwater flow within the subsurface. And there are many different types of groundwater models. The first one that is generally always created is a conceptual model, which is basically an understanding of how water moves through the subsurface. Then there are analytical and numerical models, which are mathematical models of how water is moving through the system. So this is a picture of a finite element groundwater model. I did not create this one. It's it has a lot of problems with it, but it's still not a bad, may not be a bad model. So what is a model? These are some dictionary definitions of a model. If anything, I tend to like the middle one more than anything. It's kind of like a system of ideas or mathematical equations that describe a system. So in a groundwater model, it would be something along those lines. And then as defined by the reference that you see on the bottom there, is that it's just a simplified representation of the complex world, like this cartoon drawing. So, a hydrogeologic conceptual model, HCM. What is it? How much water is in the system? How does the water get into the system? How does the water leave the system? And how does it travel through the system? And at what rates? So that's kind of what you're getting at when you're thinking about a conceptualization. Now, a mine is a very small section of a large basin-wide model, which is primarily what I deal with in permitting and in those aspects that I deal with. And on the right here, this image, you can remember Clayton Valley. Some of you might have heard of Clayton Valley. It is the basin in Nevada where there is the only operating brine lithium mine in North America. And I have clients in that basin. And so I work with individuals in this basin. So we've got water moving in from other basins, Big Smoky, Alkali Springs, and it looks like all the water is coming in. That's what these arrows represent. Where's the water going? It has to leave through evapotranspiration or evaporation. Those are the only other discharges because it's not flowing underground. It also enters through precipitation recharge, which is probably pretty limited. So moving on, groundwater model. It's a mathematical representation of that conceptual model. So here are some boring equations. The groundwater flow equation, which some of you have seen, and many people much smarter than myself have worked on solving these equations, and they produce software that I use, which does that. So here's a simple solution. This is an analytical model. It is the Tice equation, which estimates how much water or how water levels change when a well is pumping. You don't need to remember any of this. It's an equation. It'll put you to sleep. So just look at it and realize, oh yeah, there's some analytical solutions. Another really simple one is a three-point problem. It's basically, let's say you're at a contaminated site, such as a gas station that has a leaking underground storage tank. You want to know where that gasoline, that BTEX, or whatever it is flowing. It flows with groundwater. Groundwater flows downhill. So you need to know what is the slope of the groundwater table in that area. You drill 3 wells, you find the water level in those 3 wells, you fit a plane through that surface, and along that plane, the direction of steepest gradient is where that goes. So this is a simple mathematical problem to know where your underground storage leaking tank, your storage tank is leaking and where that plume is going. So this is one of my biggest, most important slides, is that all models are wrong. There is no model that is correct. All models are wrong. Whatever model it is, it might be a model of a train, a car. It might be a climate model. It might be a model of groundwater flow underneath a lithium mine. Whatever it is, it's wrong. However, some models are useful. Not all, and a vast majority really shouldn't be used, but some models are useful. They can be used as tools. And it's the degree of wrongness that indicates how useful a tool is for a given purpose. So how can you quantify the wrongness of a model? You have to look at how well it matches historical information. Does that model really represent that? And are you okay with the level of wrongness of your model? And that uncertainty that you have in a model's wrongness is a key term. Uncertainty. It's how well have you characterized what's the uncertainty in that model? How correct is it? So now let's move on to a couple projects that I have worked with. This one, Peñasquito. It is a gold mine. At the time, it was owned by Gold Corp. It's down in Mexico. You can see it here. It's in the state of Zacatecas. And we were tasked with determining the impacts of extracting water for the mine over its life of mine. That's what the LOM. So how much water did they need? They needed a total of 10,000 cubic meters of water every day. Does that sound like a lot of water? Those units, I don't understand. I've been here. I understand things in gallons per minute. So how many gallons a minute is 10,000 gallons or 10,000 cubic meters a day? That's roughly 18,000 gallons per minute. That's a lot of water that they're pumping and that they need for processing of the gold ore that they had. Now, the existing well field that they had, let's see what my next slide is. Okay, so here is the mine is up here where Mazapil is. The model that I developed, that we developed, is this kind of pink value here, and the basin that the state of Mexico, the Zacatecas state in Mexico governs groundwater is based on this basin, the kind of the green. So the mine is here, but I have to develop or use this whole area. So this is, here it is, kind of tilted. It's geologic map, geologic model, and we'll see these cross sections in a minute. The mine is right here. You can see a scale 20 kilometers. So this is a big basin. The mine is right here. Their current well field is right here. So that's 10 to 20 kilometers. They've got to pipe their water up to the mine. However, that well field only produced about a third of that water that they needed, 6,000 gallons per minute. So they were asking us, where do we find this other 12,000 gallons a minute? We developed the conceptual model based on this geology. And here's some cross sections. There's a lot of vertical exaggeration, just so you can see the various units. So we've got this gradational area. It's kind of basin fill, but it was pretty well consolidated, but it was somewhat loosely. You could break it apart in your hands, but it still felt pretty solid. And then you had more of the bedrock, which are represented by these other units. So there's water flowing through all of these systems, and I was tasked with finding a way to extract 18,000 gallons per minute. Conceptually, what happens is water falls on a basin as precipitation. Some of that water is automatically pulled up or lost to evaporation or evapotranspiration by plants. So it's evaporated, it's gone. Other of it, a little bit other, infiltrates directly into the ground. And that is, we refer to that as diffuse recharge. So it's recharging the groundwater system. And that diffuse recharge primarily happens in the mountains. Just like here in the mountains, there's more snow than there is down here in the valley. So you're going to get more rain up higher in the mountains. So that's where primarily where most of the water falls, the higher recharge events are. But the bedrock or the rock units there are a lot less permeable. Not much water can seep in. So most water, a little bit seeps in and recharges, but most of it flows down through drainages out into the basin fill, and possibly, and in this instance, they were arroyos during the wet season. They were like these caverns that would just, or big ditches, caverns that would fill up with water and flow out into the basin. And that's where most of the recharge would happen, in these arroyos. So that was our conceptualization. And then water would flow out of the basin through the ground or through evaporation or through plants. So we ended up simulating wells that were placed all throughout this entire basin, as you can see here. Each of these little circles represents an area where we would place a well. And the lines represent how water levels change throughout the life of mine. So here we're affecting pretty much the entire basin with groundwater level declines based on this pumping scenario. Just for this little mine up here. Well, it was actually a bigger mine, but it's little on this picture. So we found that yes, you can, but there are consequences. There are impacts to supplying all of this water to the mine. And there are towns represented by these little orange dots that happen to be within these bounds or near to them. There's a little bit of agriculture. So there is some impacts, and the mine would end up having to mitigate and help these towns do that. And the mine was very proactive in this. They would host community events. They were very open about things. And for the most part, the communities were open to the mine because they liked the benefits of having the mine there. Now, there were some towns, I believe this Cerro Gordo town had been moved twice already when I was involved in this project because of the dust that was getting kicked up, and there was fear of silicosis with those town folks. So a lot of people in that town got 2 new homes out of it. They had brand new homes, new water supply. The roads were paved for the mine. So there were benefits for the people, the communities. Now there were also, they had to view and see this mine being built. So what is okay? Was this okay? I don't know. They got approval from the communities and they started working on it. Now this is a huge expenditure. They probably had to put in 200 kilometers of pipe to supply that water. That's not a cheap expense. They also have to drill 50 to 70 wells. That's not a cheap expense. But there was a lot of gold in this mine, so they could pay for it. Is that bad? I don't know. It wasn't up for me. I'm just trying to figure out if there was enough water. Am I okay with it? I don't live there. It's more up to the people who live there. Is it okay with them? Now, this picture I pulled from Albemarle's website, and this is you can see the town of Silver Peak right here. Your textbook, what's the author's name? What's his last name? Scheyder? Scheyder. He says that there's 200 people that live in the town of Silver Peak. I think that might be a little on the high estimate. So what you see here is a lithium brine extraction company. They pump up the water. It's full of brine. They put it into all of these evaporation ponds, evaporate the water, collect the salts, which is all this white stuff you see here, and convert that to lithium salt that can be used. I think it's lithium carbonate, something like that. And then that is used in our lithium batteries and elsewhere. So in this basin, they've been doing this for over 50 years, since the 1960s. So I'm going to talk about the project that I've been involved in here in Clayton Valley. So in Nevada, south of us here is Clayton Valley. Again, here's this image that you saw before. Silver Peak is right here, and that's also the name of that mine, Silver Peak Mine. Again, water. How much water goes in and out? That's the project that I was involved in. I was hired by another mining company who has claims within the valley for lithium brine. They wanted to know if they could pump out, or what the impacts of their operation would be on other users in the valley. And here's a picture of court because I was involved in a legal proceeding, a water rights hearing for this. Now this picture, why are there only 9 jurors? I don't know. This is not a picture of the case that I was involved in. And when I was there, it was not in a courtroom. It was in a glorified conference room. And it was an administrative hearing where there was a judge, but there was also a panel of scientists and the state engineer who sat on there presiding over the proceedings. Then there was the proponent or the proposed action, which would be my company that I was hired by. They wanted to extract water for lithium. And so they had made application to get water rights for that lithium brine. And then the other side were individuals or groups that protested the state providing the company I worked for, Pure Energy Metals, acquiring those water rights. Now, I had no real opinions on conflicts in that case. All I did was state that I had built a groundwater model of the system, and this is what that model would predict the impacts are. Now you can find those proceedings online. They're public. All of the documents are there, and you can listen to my testimony. I don't recommend it because I'm a boring person to listen to as I sit there on the stand, but you would find out excruciating details about the Clayton Valley. So the way water rights in Nevada work is they divided all of Nevada up into all of these basins, Clayton Valley being one of them. And this was back in the mid-20th century. They estimated how much water is in each of these basins that can be used. And they called that the perennial yield. So you've got a perennial yield in a basin. How much water can be used? And that was the number that they said, okay, the state was like, well, you can probably allow that much water to be used in a basin. In the 1960s, when Silver Peak began their operation, they said, we need water, we're gonna mine, we're gonna pull out water and pull out all the lithium. We're gonna evaporate it. So we want X amount of this perennial yield. The perennial yield for Clayton Valley was somewhere between 20 and 22,000 acre-feet per year. So what did Silver Peak request? They requested 20,000 acre-feet per year. And this is the total pumping that Silver Peak has had since its inception in the 1960s. And that red dashed line represents what 20,000 acre-feet would be if they started pumping at their water right usage. Now, one of the rules in Nevada is, or one of the things they try to prevent in their laws is water hoarding, water speculating. So you get a water right and you hold on to that with the idea that at some point in the future, somebody's going to want that water and we'll sell it to them. We'll sell that water right. So Nevada has a use it or lose it rule. If you don't use it, you lose it. Now there's a lot of legal ideas, and I'm no lawyer, so I can't talk to that. But potentially it could mean that Silver Peak, they haven't used that water, it might be lost to them. But there's also the point of view that if you have a water right, you're trying to use it, trying to put it to beneficial use, you're using some of it, you're just not using all of it yet. So you can apply to extend that water right. So 20,000 of a possible 22,000 is on paper is being allocated to Silver Peak. So the company that hired my company was like, we want to use some of this water, but we can't do this with evaporation ponds because there isn't enough water in the basin. There are other water users. Town of Silver Peak needs water. There are people that live there. There may be less than 200, but there's still people that deserve clean, good water. And we want them to have their water. So company that hired us had developed a novel approach to extracting lithium from brine. So Pure Energy Metals and their parent company teamed with a company that they're currently branded as SLB, which happens to be Schlumberger. So if you know who Schlumberger is, if you've heard them, they're a very big oil and gas company, drilling company. So they, in cooperation with Pure Energy, developed a direct lithium extraction method. So essentially it's you pump up the brine, you run it through a system, it pulls out the lithium, and then the spent brine that has no lithium in it, you put it back in the ground. There's a little bit of water use within the system, but not much. So you put that water back into the groundwater system. So how much water is actually being used? What we were asking for was being able to pump 12,500 acre-feet per year, which is a lot of water. But the proposal was to put it all back into the ground, or at least 10,000 acre-feet per year of that, and only consume 2,500 acre-feet. So that's essentially what the water right request was, 2,500 acre-feet, a small amount. That hopefully there was some left. So if Silver Peak continues using at most 14,000 acre-feet, there still might be some left in Clayton Valley for Pure Energy to use theirs. And so Silver Peak or Albemarle is this blue area here. That is their claim. And Pure Energy Metals is pretty much everything else. Now, these aren't the only two claims in the basin. We work for, I think, two other parties within that basin, trying to get at the lithium. So, like I said, direct lithium extraction. And this is the pilot plant that SLB built out on Clayton Valley. Off to the left of this figure is where the Silver Peak operation is. You remember seeing that picture with all of those ponds, and this is the footprint of the direct extraction lithium. It's much smaller, water is not consumed, and it's directly put back into the groundwater system. So, did my client get their water rights? I have no idea. The state engineer hasn't issued his ruling, and that was, we finished up the court case, or the case, last May. And closing arguments haven't even been submitted. They're submitted in written form. So we're at least a year away from when the state engineer is going to issue that ruling on whether or not Pure Energy gets their water rights. Hopefully, we'll see. If nothing else, SLB and Pure Energy has this technology now that they've tested, direct lithium extraction. And I believe this is the first direct lithium extraction pilot plant in the world. I don't know of any others. There's another couple of companies that are developing it, but I don't know if they actually have it. And it worked. It was nice. They were, at the end of this, one of the SLB employees showed me a little vial of the lithium that they had pulled out. It was just a little bit, some of the initial salts that they were pulling. So this is getting me excited because lithium brine, one of the big problems with lithium brine is the amount of water consumption. Most of the lithium brine is occurring down in Chile and Argentina, where you have these huge evaporative ponds in an area that gets less than 100 millimeters of rain a year. So all this water they're pumping up and evaporating. So a direct lithium extraction operation there could save a lot of water. And it was interesting that part of that water that is consumed, they take the brine, they run it through their system, and the spent brine goes down, but there is a little bit of water that is consumed. And what that water comes out as, it comes out through almost like a reverse osmosis system. So it's perfectly clean, drinkable, potable water. So it's coming out. So it would even generate a source of potable water in these areas, or it could. So next I want to talk about NEPA, National Environmental Policy Act. So as you're reading that book, you're going to find a lot of references to permitting. Now, when it talks about federal permitting, he is referring to and alluding to the National Environmental Policy Act, NEPA. So what is NEPA? NEPA is all about impacts and disclosures. You have a project. What is your project going to do? And what are the impacts of that? Disclose those impacts. Do studies that determine what those impacts are going to be. And it's not just, from my perspective, groundwater, because that's all I look at is the groundwater. And I've done a lot of NEPA baseline and NEPA writing work recently. There's a whole lot of resources. I deal with water resources. There's a geochemical aspect to that. There are biological resources, there are visual resources, there's archaeological resources. All of these resources need to be evaluated for a NEPA study. So one reference in the book, I believe you guys are through chapter 4. One of the references in your book is that this NEPA process is being rushed. And I like to caveat that. It is what was referred to is that the BLM was having to rush through the permitting approval over a given year. And it almost made it sound like all of the studies were needed to be done in that year, which is not true. Baseline studies generally start 10 years, 5 to 10 years before you even get to that permitting. So what I work in my field is getting those baseline studies up and done so that when you get to the NEPA analysis and that permitting, it's not faulting, it's not lacking anything. And so the regulators can make their choice and make their decision on the baseline studies. So this is just the cover from one of the baseline studies that I did a long time ago. Well, I don't know, 15 years ago, from Bald Mountain, another gold mine. So what are the potential impacts that your project will create, and tailor your studies accordingly? So this is another key slide when you're looking at NEPA studies. Baseline for groundwater or for water resources. These are the things you guys need to look at, or the things that need to be reviewed. For water, how do water levels change? Pits, underground, what are those impacts? All of those things. And then on the right, the typical studies, surface water surveys. So where are the streams flowing? When are they flowing? What are your seeps and springs? What are the flow rates? What's the chemistry within those? And those we typically do twice a year. Once in runoff, high spring or high runoff in the spring, high snowmelt. And then in the fall, when it's typically just baseline, when all the snow has melted, there is no runoff. And we started a project and we did one of these surveys in 2023. Can anybody remember what the ski season was like in the winter of 2023? Do we not have skiers? It was pretty decent. Yeah, I live in Salt Lake and we had over 600 inches of snow in some areas. There was a lot of snow in 2023, and that's when we started these studies. So do you think a baseline study in the spring of 2023 was pretty accurate of conditions? Probably not, right? So multiple years of this study is probably needed so you know what a true baseline is. And so we went out again this last year. And then every year after, we're going to be doing the same survey, going to these same seeps and springs. But for a lot of us, that's why we got into this business. So we could go out and hike the mountains, get chased by mountain lions, sample springs, and call it a day. So we do hydrogeologic characterization, put in wells, do studies, geologic mapping, groundwater modeling, materials characterization. What that constitutes is basically geochemistry. What is going to happen when water hits this rock? And eventually it will. So this is a project that I've been working on probably on and off for the last 4 or 5 years. So here is a picture, and this was taken from the I-80 website, I-80 Gold. A real novel name, I might admit. Can you tell where this mine is? It's off of I-80 in Nevada. Anyways, this mine, it was mined in the 80s and 90s, and it finished up in 2000, 2001. And so all the water levels recovered. And can you guess? The pit filled up with water. It's about 700 feet deep right now, and it's still filling. So that's a lot of water. And it's really pretty, isn't it? That blue, I like that. And the water quality isn't bad either. You could probably, if you got enough microbes in there and got some sort of plant, you could probably stock that with fish. I would get in that water if I wasn't worried about stability of the pit wall. So there's this, but I-80 has bought this mine, this old mine that's been closed for over 20 years. Why? Because underneath that pit, there's still more gold to get at. And you can see it on the left. There's the Helen on the left, that yellow and pink, and then the green is the Gap. And then there's some other deposits off to the right there that are there, but they don't have plans to mine those yet. So they want to get at this stuff on the left. So what do you got to do to get to that? You got to empty that pit of water first, right? That's a lot of water, 700 feet of water in the pit. And then you've got to dewater the ground around that. So that's a lot of water. We developed a conceptual model. Here's the geology. Seeps and springs. You can see those purple ones are the ones that we look at and we monitor. We've done an aquifer test. These are all the locations of that. We've done multiple aquifer tests out there. We've built a groundwater model, and these are some of the results. Remember, what did I say? All models are wrong. But is that wrongness acceptable? And you look at that, the model is the blue line, the observed are the circles and the darker blue. And it matches reasonably well. We thought it was okay for the purpose of this. And this is from when it was mined originally, back in the 80s and 90s. That's what this data is. And so we were able to reasonably match that. And we thought it was okay, so we use that to do predictive modeling. Now, because this project is just about to enter into NEPA and go through that permitting process, I can't show you results of what the predictions would look like because it's not public yet. But the results would look something like this. This is another mine about 50 miles or 100 miles east of that other one. And it shows the blues are where water levels are going to be depressed due to dewatering. And the yellow is where they discharge those water to basins that just infiltrate in. And this is historically what that mine, that Pit Lake mine, they discharged water on the order of 10 to 16,000 GPM into these basins, and it infiltrated back into the basin. And for this project, it's going to end up doing something similar. Probably because they're going deeper, they're going to end up with much more water than just this for this next phase of mining, to dewater that pit lake and then get to this. So the last project I will finish up in just a couple of minutes. This is another EIS, environmental impact statement. So it's about impacts. So there's this mine right here that's proposed. Now there are other mines that are nearby, a very similar proposal. And this is to mine Trona. It's an in situ mine. So here At the bottom of the Wilkins Peak, or into the Tipton member, the bottom of the Wilkins Peak, there are some Trona deposits that they want to mine, and they want to do in situ mining. What does in situ mean? In place. So they plan on, these are cross-section views of drilling a well, 2 wells down into the system, and then another directional well. This is 3,000 feet down into the ground. They're going to make it turn and go horizontal and intersect these other 2 wells. So that's going to take a lot of engineering to do that. And then you just pump water into there, into these 3 wells, and dissolve the Trona, collect the solution, and process it above ground. These are the impacts, how far out drawdown will extend in the various units within the aquifer. And here is Flaming Gorge. And so they're interested in what are the impacts of Flaming Gorge and where are they getting water from. They're actually going to take water from the Green River and pipe it out there. Now this figure is a little misleading because it is, I believe it's the cumulative impact. So it's not just how much water level drawdown is going to happen from the single Trona project, but the other 2 Trona projects in the area. What are the impacts going to be? If all of them happened at the same time, how far out would this water level change occur? So it's important to know the difference between the 2. Lastly, different perspectives. One of my mentors stood atop a mountain much similar to this picture here, looking out over a large mine. And he was with a tribal leader. And the tribal leader says to him, "This is ugly. This is a monument to human stupidity. Why did we make this look like this?" Whereas my mentor replied, "I see something very opposite to that. I think this is a monument to human ingenuity and to our ability to accomplish things. We've built this. It's a symbol of our progress. It's a beautiful thing." There are different perspectives. I hope that, especially in the water world, that I've been an influence of bringing those 2 perspectives, or 2 different perspectives together, where we can, yes, agree that it is a monument to something and that we can move forward with it. So I think there is some common ground. There can be some water, and the way the system that we have for that currently in our country is NEPA. What are the impacts and are they acceptable? So your discussion topics, I went a couple minutes over my 40, I'm sorry. So when you evaluate a new mine, what type of groundwater issues should be evaluated and why? What is the difference between a cumulative impact and a project impact? Why should each type of impact be involved or evaluated? And lastly, what good are models and how would you evaluate a model?
Thank you, and we'll take our little break. And while during that time, we'll have our discussions around our tables. And those remote may choose to join the one breakout room. And if you're remote in our class, please do so for sure to talk about the discussion prompts. And we'll see you all in 5 minutes for the open Q&A.
Okay, folks. Yeah, there was that dreaded dip in the room volume. You folks should all have been around college long enough to know that that's a giveaway for professors, right? Okay, so I'm going to run the mic. Ajay, you will let me know if anyone has a question online. Otherwise, let's get this show on the road. Questions for Greg? Going once. Hank. This is 2 parts.
I just got a single in this then. So you mentioned in Nevada, they have, they've managed the groundwater, I take it, is what we were talking about. So how accurate was their estimation for perennial ingress? Yeah, and then compared to what you found?
We're going to let you keep this, and I'm going to ask you politely to summarize questions for the folks online.
Okay, so in Clayton Valley, for that case that I was involved in, the state perennial yield is 10 or 20 to 22,000 acre feet per year. My work, and I have to remember that I did not testify in that case in regards to the perennial yield. I simply assumed that what the state had published was correct. Now, there were other estimates that others presented that ranged from 8,000 acre feet per year up to 18,000 acre feet per year. And as a result of, primarily as a result of this case, the state is starting to do studies throughout the state to update those numbers from the mid 20th century. Now, that study that estimated that 20 to 22,000 was done with approximately 2 weeks worth of field work. So it was a very limited study. So you can guess as to the uncertainty and the bounds, the min and max bounds on that range of what that 20 to 20,000. So what that is, I don't know. I'm letting the smart people at the state of Nevada tell me if it needs to be revised. But there are indications that they might adjust that. Now, I just wanted to add one more disclaimer. Many of the projects that are described in the book you're reading, I've worked on directly, or I know people who have. So if you have a specific question about any of those projects that you've read about, go ahead and bring it up and I can talk to whatever knowledge that I have. For example, I've worked on Resolution, the Resolution copper mine. I've worked, done a little bit with Morenci. I was going to write the water resources section of the EIS, the NEPA project for Twin Metals Mine. So if you've heard that one's in Minnesota. So there's a lot of things that I have direct knowledge of that you can just pick my brain about if you'd like. So next question.
Extraction, sorry. And I was wondering, where does that extra bit of water, the 2,500 gallons that are used up in the process? I feel like that was kind of glossing over something. Where does that water go?
Okay, the question is talking about the direct lithium extraction. Pure Energy would pump out 12,500 acre feet of water. They would extract the lithium and then inject 10,000 acre feet back in. The 2,500 acre feet, the question is, where is that consumed? Where does that water go? And when those applications were filed, they were all theoretical. So it was, okay, we're going to pump it out. We're going to use DLE, direct lithium extraction, and put it back in the ground. Well, how much is it going to go back in the ground? They didn't know. They made a conservative estimate that it would be approximately 2,500 acre feet over a given year. Now, a lot of that depends on how well can you inject this water in. So their request was, we're only going to consume 2,500 acre feet. And it could be that that water just becomes that potable water supply that's there. Or it's consumed on the site via dust suppression. So you put it into a water truck, they drive out and they spray that water onto the roads and it keeps the dust from when a car drives by, dust kicks up. Those of you who have driven on dirt roads know that that can be an issue, kicking up a lot of dust. So the mines use a lot of water in dust suppression. Or it could just be consumed in the process. It might be that the water ends up with a chemical or some constituent in it that can't be discharged into into the natural system. And so they hold on to it or evaporate that water. So it was just the allowance for the process and what that actual rate might be. It might only be 2% of the extracted water is used or consumed, or it might be up to that 2,500.
I've got a couple of questions, but I'll stick with just one for now.
Excellent plan.
But these two sites look very close together because they're on the same project. On the Trona mine, Wyoming, is it common for those three mines to have been lumped together? And do you know why they were lumped together in this situation?
Okay, so the question is, in that Trona in situ mining, there are 3 mines that are all nearby. They're all doing in situ mining of the Trona deposits. And is it common to lump them together? In part of the NEPA process, you must do a cumulative impact. So any reasonable and foreseeable action within the area of the mine or in the area of the proposed action needs to be considered. So what are the impacts of all of those together? And so that's why they were lumped together. So you need to say, what are the impacts directly from the project? And then everything else altogether, what are the impacts? So all of those mines together, what are those impacts? With the example of that pit lake that's going to get dewatered, there's another mine that's about 15 miles away that those impacts will need to be considered. But also there's agriculture out in the basin, out in the valley. That will need to be considered in the cumulative action. How much pumping? What is the water levels related to that? So that would need to be. There's potential for a geothermal project on the other side of that project. So what are the impacts to the geothermal system that are caused by that mine? And what are the impacts of that geothermal process, if that happens, on the mine? So all of those things. So it's meant to be more of a comprehensive understanding of what the impacts are. Thank you, Mark. Great question.
So, you mentioned that you take kind of a hands-off approach to a lot of the ethical issues raised by some of those minds. Am I okay with this? I don't know, that's for the local people to figure out. And I understand that can be the nature of consulting, you're doing hires to deliver a specific product. Do you or your firm ever take more active, ethical framework to the work that you do in delivering that product, or do you ever turn down any kind of work because of ethical concerns?
Yes. To summarize your question, you can correct me and tell me if I'm wrong, is that I mentioned when talking about Peñasquito that I take a hands-off approach, that on deciding whether or not to move forward with that project and the impacts to those individuals, I let the choice be to those individuals. And that could be construed as a ethical choice that I make. Is there ethical reasons and ethical choices that I and my firm make in regards to projects or work that we do? Have we turned down work in regards based on for ethical reasons? Is that essentially the nature of your question? More or less. Okay. So in regards to Peñasquito, we were contracted to determine what the impacts would be. And there were some impacts that, or some instances where we looked at and said, this would not work based on these circumstances. And it would be too harmful to this group or this town or something like that. So those things we brought up, we said, we don't agree. We don't think this would fly with any regulator or with us for that matter. So there is those concerns. Yes, we do make those types of distinctions. But when we get it to a point where this is the least impactful solution to the problem, and that's also what NEPA gets into. In NEPA, you have to analyze different alternatives. What are some other options that could be done for this proposed project? And the process that the regulator, the agency in NEPA determines which of those alternatives is best. And along the lines of how does ethics play into the work that I do? I am a registered professional geologist. And as part of that, I had to pass an ethics test, essentially, what the professional geologist. There is a little bit of science in that test, but a lot of it is nuts and bolts ethical questions. This happens, how would you do it? How do you react to this situation? And so there is a lot of ethics that come into play. So yes, I am bound by ethics, and I do make that decision. And it's, I was torn for especially the Twin Metals mine. I don't know if you've gotten into any of that in Scheyder's book, but that mine is proposed to be underground, right downstream from the boundary waters in Minnesota. And the mine actually goes below and underneath a lake. And it's this pristine, it's one of the most visited outdoor places in all of America. Am I okay with that? I don't know. I still haven't come to an answer to that question. I am happy that I don't have to make that decision anymore. I don't have to look at that. I was hoping to just look at the scientific reasons of that and say, this is what the impacts would be, and let the BLM or the Forest Service, or I can't remember who the agency was, make that decision.
In your turn.
You mentioned something like certain models, like entities and ways that they should be used. Something along those lines. I'm just curious in your work, especially when you think about these things like Clayton Valley, where you have your data model on the one side and then also the protest. Like, how often are you seeing like your modeling getting challenged by folks doing other modeling, and how it gets resolved? I'm just curious about the values of the model. How much that comes into play.
Okay, the question was, in Clayton Valley, in that case, there was a lot of, I developed a model, and so there's a battle, there could be a potential for a battle of models. The other sides, the protesters in that case, did not present their model. But they did cut holes in my model, which were valid. And if you want to find out what they were, go ahead and read that or listen to that transcript. I'm sure you can find it online. Again, you'd be bored out of your mind. But still, there were holes in my model. And the nice thing about that format for that hearing was that I gave my testimony. Those that opposed it, the lawyers were able to ask me questions, and then it went to the state. So the state had this whole panel of scientists, and they were able to, and then we were just able to talk on the record. They asked me questions about it. I answered. We had this discussion about the models and how useful it was, how useful those models were. And that model that I did, I had a limited amount of time to build that model. And so I did no calibration of that model. So it was purely a deterministic model. It was, this is what I think it is, I'll put it in, and that's what it is. So I didn't check it to see how well it matched water levels. I just said, oh, it matches this soft knowledge. The water, we know that the water table is close to the surface. And as long as the model represented that, it was fine. And we moved forward with it. So, like I said, all models are wrong. That was a fault of that model. But was it useful? That model allowed the state engineer and his hydrogeologist to make changes to the conceptualization. Okay, well, what if that perennial yield isn't 20,000? What if it's really 13,000? You could change that in the model that I built really simply, and they could use that as a tool to test what would happen if that were the case. And so there will always be competing issues. A lot of times models are asked questions that they shouldn't be asked. A model is built for a single purpose. And once you get beyond that purpose, you start to get into, the model might be a little too wrong for that purpose. So it gets into, what is the purpose of your model build, and does your model meet that purpose?
Got Ian and then Mark, I think. Yeah, anyone else just sort of flag me now? All right.
Well, this kind of continues to that. So since models are wrong, they're just an estimate. I guess we talked about the pre-permitting procedure where it's like, well, we're working to get a permit. What happens once you get a permit and the model says it's going to do this? Is that kind of a guardrail at that point? And who kind of follows up to make sure that model is accurate? And like you guys work on that front where if a mine starts doing something that has adverse impact, you guys can suspect that they like reanalyze and kind of make a new permitting procedure to spread it out further.
Okay, so the question was, so you build a model for a permitting process. The mine gets the permit and moves forward. What happens to the model then? Is there kind of a reevaluation and just check to see if the model was accurate and right? Did that model, the predictions from that model actually pan out in what actually happens in the permitting? Is that right?
Yeah, and is there guardrail?
And guardrails if it doesn't. So generally what happens is when the permit is issued, there are stipulations to the mine that they must update that groundwater model according to what happened in the past and their current mine plan. Because mine plans are going to change, and that's allowed in the permitting process to some degree. And so as that changes, the groundwater model needs to be updated. You're getting more information, you've got more water levels, more testing, so that continually gets updated, and that's usually mandated within the permit that is received. And it usually involves updating the model, updating the baseline studies, and present reports to the agency or to the public. And I have found that more often, it's not the federal permits that require that. It's usually the states that require that continuous update. And I've seen instances where it's every year that model needs to get updated, which is great for me. It means every year I get to redo and update a model, more work for me, or it's every 5 years, which is usually probably what is best suited in the industry. The model becomes public. All the modeling files become public during the permit process. The state has those, and my firm, I don't even view the model as owned by my firm. It's owned by whoever pays me for it. So it's the mine's model. The mine owns that, and I give all of the modeling files to them.
Thanks, Ian. I think, Mark, we've got you, and then we'll reopen the queue.
I want to go back to a resolution for a second. I know you're familiar with it. The question that I had is kind of around the water rights. I'm assuming that Oak Flats has some water rights just on it itself. And from my understanding from Scheyder is that the idea, if they open the mine, is that the data pairs in the past year are going to be able to go and use Oak Flats for a couple of decades at least until the tail talks. And I assume that that's going to provide an extreme challenge to water will safe enough to have a reasonable chance of maintaining that aesthetic climate.
Okay.
My question is that general.
Okay, the question is regarding resolution and Oak Flats, which is the area where the mine, beneath which the mine would be. And what will happen to the mine after it's mined is that over some period of time, the ground will subside into a giant crater or cavern, or not a cavern, just a giant crater. And that's to happen over a couple hundred years or so. So that would happen, but in those for the first several decades or so before the subsidence really begins to occur, the Apache tribe would be able to use Oak Flats. And the assumption is that there's water rights that the Apaches would have and be able to use at Oak Flats. And the question of tailings and the tailings being full of constituents that might be harmful entering into that groundwater system. Now, the correction I'd like to make is, first of all, that the tailings will not be in Oak Flats. The tailings will be discharged in other basins, in other areas, so that tailings water would not be influencing that mine area. And there are a number of alternatives, and I believe the preferred alternative was Skunk Camp. And that is on another basin, and there are concerns about the water quality of tailings seeping from that and getting into the groundwater system and flowing downstream. And those, how far those constituents move in the groundwater, I believe is held within the EIS, that environmental impact statement, and it lists and it shows how far those constituents would move, but those would not impact the Apache and Oak Flats. And any mine I've ever been involved with, if they impact a water user such that they no longer have access or use of their water, they provide another water supply, a water system.
Going once. And twice. That looks like we are right at time, so join me in thanking Greg one more time.